Okay. All right, February 5th. All right, so today's class is today's class is coaxial cable, multiplexing, broadband, and baseband. All right, now let me just give you some little kind of idea here. When you get the when it comes to using links, wire, especially wires or cabling, because you can also use air as far as electromagnetic waves, so you can use antennas to transmit the signal, or you can use fiber optics to transmit light, and there are different principles involved when it comes to that. But when it comes to using copper, one of the biggest challenges is to overcome crosstalk and interference. We're going to cover that in the next couple of weeks as far as crosstalk. But basically, crosstalk is the signal bleeding through one pair of wires through another. Right? And one way is to use a twisted pair. So when you twist the cables, twist the conductors in a pair, the magnetic field that goes around it basically disperses. And then you have another pair beside it, and you also twist that pair, twist it at different rate, then there is less of a chance of the magnetic field produced by one pair of cable entering and by induction and affecting the other pair. But we are going to, that is going to be a topic for the next couple of weeks. Now, today we're going to talk about coaxial cable. Now, so when we're talking about the twisted pair, so that's one thing. The other way of eliminating crosstalk would be, here's another idea. Let's say there is a conductor that, can we see it? Yes, we can. Involves two conductors, and one conductor is the outer shield, and the other conductor is another wire that is inserted into the other conductor. So it's a conductor inserted into another conductor. So the wire that goes inside provides the signal path for the signal. The other conductor that is around, that's embedding that conductor, provides return pathway for the electric current and also acts as a shield. Now, these two conductors, the outer conductor and the inner conductor, they share the same axis. Okay. That's why we're calling this thing coaxial cable. Coaxial cable, all right? Because they share the same axis. Those two conductors share the same axis. Sometimes it's also called concentric cable. Coaxial or concentric, they're both the same thing. However, the coaxial terminology kind of stuck around a little bit better than the concentric, but that's the same thing. All right. Okay. Now let's get to our lesson here. Switch that. All right. So that's basically what it looks like. Here is the outer shield that's connected to the connector here, and that is actually connected into the inner shield, the outer shield of this cable. And here is a inner conductor. All right. That's what it looks like when you take it apart. So over here you have a center conductor, right? And you have a braided shield and a foil shield. Sometimes you just have the braided shield, and sometimes you're going to have just the braided shield. And this is just another visual representation of that. So just a little bit clearer. This is a picture of it, and this is somebody drew this thing using some graphic software. Okay. Now the question is, you will probably need to rewatch it. Okay. Now here's a question here: why is there so much protection? Well, there's no. Okay, I'm going to answer that way. There's never enough. Okay, even when you deal with copper, even if you try to get as much protection as you can, you're always going to have some sort of interference because copper wiring is susceptible to magnetic interference. And even in the smallest amount, always something is going to get through into the cable and something is going to get out of the cable. We don't have that problem with magnetic interference when we're dealing with fiber optics, but we have other challenges to deal with. Okay, so that's why we need so much protection here. Okay. All right, so a coaxial cable is a two-conductor cylindrical transmission line, typically comprised of a center conductor insulating dielectric material, which is an insulator, and an outer conductor shielding, outer jacket as well. Where we use this cable is cheap. We use this cable, we use this cable because some systems it was established some time ago. And with some systems, it's actually more efficient to use coaxial cable. In some systems, it's more efficient to use twisted pair, and sometimes it's more efficient to use fiber optics, and sometimes antennas. It just depends on the system and the equipment that was produced for it. Okay. Now, okay, so just a bit of a background here. A series of stranded types of coaxial cable were specified for military uses. That was during the World War II when there was a need to transmit signal or convey signal over something. And part of it involved maybe not using antennas, because antennas produce signal that could be picked up just by anybody. But when you use a coaxial cable as a radio guide, then you have the signal contained. Plus, when the radar was developed, something was needed to convey the signal from the transmitter onto into the antenna in a some sort of efficient way. So that's why this thing was invented. Okay, now RG, the designation of coaxial cables, you're going to see RG, different type of RGs, and the RG stands for radio guide. Now, I'm going to show you three types of how they compare to each other. Here's RG59, RG6, and RG11. Now, when you get to the numbers, those numbers do not mean anything as far as specifications. Consider them as names, okay? So somebody developed a certain type of cable that behaves a certain way, and they had to standardize it and classify it and had to name it somewhere. So they just decided to use the numbers for the classification of the cable here. Now, RG59 is slightly, okay, so let's start with the RG6. So RG6 is basically the cable when you have a cable modem installed and the technician comes to your house installing the cable modem, that's the thickness of the cable. That's the RG6 that you're going to see. Right. Now, RG11 is much thicker. Basically, that's how it compares as far as thickness. And it's more efficient, but it's also more expensive, and it's a little bit more difficult to route and put connectors on. Then there's RG59, which basically behaves almost like RG6, but it's thinner, less expensive, and for shorter distances and when there's not so much demand on the bandwidth or signal losses, then if you can get away with RG59, then it's just less expensive solution here. Now, one thing I haven't listed was RG58, and we're going to talk about that as well. All right. Now, there are so many, there are a lot of RGs, okay? I just want you to know some of the differences between RG59, RG6, RG11, as well as RG58, which is not listed here. Now, we're going to spend some time on some of the main specifications. Joined late, can't hear anything. Jonathan, yes, there is audio. I hope you can solve it. If not, you'll be able to watch this on YouTube, okay, and have the post-it notes. So it's not me, it's you. Okay. All right. So when it comes to dealing with coaxial cables, one of the main specifications I always going to hear is going to be the impedance. Now, when it comes to impedance and coaxial cable, uh, people are going to talk about impedance. What's the impedance? What's the impedance for the coaxial cable? Which impedance do you need for this type of equipment? When they say impedance, is that really they mean something that's called characteristic impedance. There's a difference between impedance and characteristic impedance, and we're going to talk about that. So first, now this thing is going to help you with your other subjects as well. Well, it's all interconnected. So pay good attention to the next probably 12 or 13 or 14 slides that we're going to have. First, for me to explain to you what characteristic impedance is, I want to talk about first what impedance is. Okay, so impedance. All right, I'm going to read some of that stuff that I wrote, and I'm going to stop and go as far as explanations. Okay, so consider a linear component such as resistor. Changes to the frequency of a source. So if you apply frequency to a resistor, it is not going to affect the resistance of the resistor. Resistance of the resistor is constant, no matter what you put through it. You put AC or DC, it's going to have a constant resistance. The resistance is not going to change. It might change a little bit if the resistor heats up or cools down, but it has nothing to do with the frequency applied to the resistor. Okay? So changes to frequency of the source do not affect the resistance of the resistor. The circuit is considered as linear. The resistor will oppose the current flow in the same way, no matter the frequency. Current opposition equals resistance, and with the designation for resistance is R, as we most of us know already. Now, consider a non-linear as opposed to linear component such as capacitor, okay? Now, to a pure DC source, the capacitor acts as extremely high resistor. If you apply DC source into a capacitor, the current is going to start flowing in the beginning, and then it's just going to stop. It's just the capacitor blocks DC. So a pure DC source to the capacitor acts as extremely high resistor. The resistance is infinite, broken wire, or an open circuit. Okay. As the frequency of the source increases, or as the frequency begins to happen, should I say, right? Then the capacitor's opposition to the current decreases. So as you apply frequency to a capacitor, and the higher the frequency, the less resistance the capacitor is going to give you. Okay. Now, current opposition for the capacitor is called reactance as opposed to resistance. All right. It's because the capacitor is going to react differently depending on the frequency that you apply to it. So it had to be named something. So we call this reactance. And with the capacitor, we call this thing as a capacitive reactance. And the designation is XC. And here's the formula. It's 1 over 2 pi, whatever the frequency is applied and whatever the capacitance of the capacitor is, whatever the value is, okay? So that's a capacitor. Now consider a nonlinear component as well, such as an inductor, okay? A coil. To a pure DC source, the inductor acts as an extremely low resistor. So it's just the opposite of the capacitor. You apply DC to a capacitor, it stops the current flow. You apply DC to a coil or inductor, it is just going to act as a straight wire. As a low value resistor, the resistance is nil, and it's a straight wire, just like a short. As the frequency of the source increases here with the coil, you apply frequency, then the coil or inductor is going to create an opposition to the current flow. And the higher the frequency, the more opposition the coil is going to give you. So it's the opposite of the capacitor. You increase the frequency with the capacitor is going to give you less resistance, there's more current going to flow. And with the coil or inductor, as you increase the frequency, the resistance of the coil is going to increase. So the current opposition for coil is called also reactance, because it's not a constant. It is going to react differently depending on the frequency that you apply. So that's why we call this thing inductive reactance. And the designation is XL, that's inductive reactance. And you see the formula is 2 pi FL, where here's F is frequency and L is inductance of the coil. Okay, in all cases, the resistance and reactance, the units, we express them in ohms. Okay. Right, resistor. Resistor is a linear component because its resistance value remains unchanged if the frequency increases or decreases. Okay, so just a summary of what we said. Capacitor is a nonlinear component because its resistance, and I put that in quote because it's really a reactance, its resistance or opposition to the current flow changes if the frequency changes. In a nonlinear component, you know what? I just copied the same thing here. So yeah, well, ignore the second one. Okay, because the resistance of this should be basically a inductor. Okay, so because the resistance of a nonlinear component is affected by the frequency changes, we can say that the capacitor or inductor has a reactive resistance. We call this reactance. And here are the formulas. So this is just a review from the last slide. Now, I built a circuit in the multisim, and if you have access to multisim, and if you don't, ask me how to get it, and I'll help you with that. You actually have access to multisim software, or you can just go to some of the homework labs, and you can just fire it up in one of those machines, and you can build circuits and analyze them. Okay, so what happens here? I just built a circuit that consists of an AC source or function generator. There's a resistor just to provide some current limitation. And then we have a capacitor. And I basically turn the whole thing on and I connect an oscilloscope. So on the bottom here, on the bottom graph here, now I'm just going to switch to the next slide because it's a magnified version of the same thing. I know that Zoom, when we have more participants in the Zoom, the more participants we have in the Zoom sessions, the bandwidth is being shared. So so the video signal becomes a little bit blurry. So that's why I magnified this view here. So what do we have here? On the bottom here, we have the supply voltage, and I put a square wave just so we don't have any gradual transition. So basically, all of a sudden we apply the voltage, carry it on, and we go to zero, and so on. Okay. So what's happening in the in the capacitor RC, so RC circuit here. This is the current, the red one here. This is the red graph is representing the current over the whole circuit. And this blue line here, that represents the voltage across the capacitor. Now, I just want you to pay attention to the relationship between the current in the circuit and the voltage across the capacitor. Now, when we apply any kind of a DC, so zero is a 0-volt DC basically, right? Now, all of a sudden we apply change. Capacitors love change. They just love change. They don't want you to stay constant. They don't want you to stay the same. If you change all the time, the capacitor is going to talk to you. And if you don't change, the capacitor is going to ignore you. So all of a sudden we have a jump from 0 to whatever voltage it is here. And the capacitor is going to react to you by conducting current see there's a spike. The current goes high right in the beginning. Now as the capacitor charges, the current decreases, and if you don't change anything, the current is eventually going to stop flowing. So of course, the voltage, when the current starts flowing at its maximum, so it's just basically almost like a dead short to the circuit. So of course, the voltage across the capacitor is going to be zero because it is a maximum current. The capacitor acts just like a short wire. And as it charges, the voltage builds up on the capacitor. And then as soon as the voltage builds up to the maximum, then the current stops flowing. See that? Then we change the voltage again. Here's another change. So the current flows the opposite way at its maximum, and as the capacitor discharges, or basically goes to whatever the supplied voltage was, to that level, then the current stops flowing because it discharges. And it just repeats like that if you apply a signal like this, okay? Now, one thing I want you to notice that with the capacitor, because it acts as a short circuit, the current is first. That's an important concept I'm trying to give you here. It is going to help you with other subjects. Okay? So in the capacitor, we have current happening first, and then after that, we have voltage happening across the capacitor. Again, the current is first, and the voltage happens second in the capacitor. So you can say that the current leads the voltage in the capacitor, or the voltage lags in the capacitor with reference to current. Okay? So that's the capacitor circuit. All right, now, here is a circuit that I made, another circuit in the multisim, that instead of a capacitor, I have connected a coil. And you can build that circuit and connect that and turn it on just the way it is, and you're going to get the same results with multisim. Right? Now, with the coil, it's just the opposite to the capacitor, and I'm going to show you how. Here's a magnified version of the oscilloscope view. So I'm just going to get, this is the first half of the cycle here for the coil. Now look at this, what's happening here? Here we have the supply voltage, which is this, that's the green line. All right. Now, over here, the red line is the current that's flowing through the coil, or through the whole circuit, as a matter of fact. And the blue one, the blue line here, this one is the voltage across this coil or across this inductor. So what is going to happen? As soon as we apply, the inductors do not like change, as opposed to the capacitors when they just love change. Coils or inductors, they want things to stay the same. Just the opposite to the capacitors. So when all of a sudden there's a change, the current is not going to flow right away. The coil is going to try to oppose the current flow as much as it can. And then if this thing doesn't change, the coil is going to say, okay, so you changed it into that, but okay, if you stay that way, I'm going to let you go, and I'm just going to start conducting the current. So, so it's the opposite of the capacitor. So here's the change. No current flows at the beginning, but there is a big voltage. But of course, if there is no current flow, it's like open circuit, there is going to be a voltage across here. Okay. So the voltage is high, and then slowly the current begins to flow, and then the voltage goes down. Right? So in the capacitor, first we used to have current and then the voltage. In the coil, we have the voltage first and then the current flow. Yeah. Now here's the side by side, or one under the other, just if you want to compare that. See that? In the capacitor, the current, here's the current, it flows first, and then the voltage. So current is first in the capacitor, and the voltage builds up later. In the coil or inductor, it's just the opposite. Current flows first. Sorry, the voltage builds up first, right here. Here's the voltage, and then the current starts flowing. All right. Now, here is the graph of the inductive reactance and capacitive reactance comparing to each other. Okay, so what do we have here on this graph? Over here, we have the frequencies. Here's a low frequency. Here, the frequency gets higher. So let's say this is 10 hertz, this is 200 hertz. And over here, we have the impedance, or you can just substitute this thing with a reactance on this y-axis here. Okay. So let's say here the inductive reactance, as the frequency increases, as we talked about, the more frequency you apply to the coil is going to oppose it more. So if it's a low frequency, the coil conducts nice and easy. You increase the frequency, the coil starts resisting. Okay, it just goes like that. Right? Okay. Now, when it comes to capacitor, the frequency is low. The capacitor is going to oppose the current flow more. And as the more changes to the input of the capacitor or across the terminals of a capacitor you apply, the more often you get the change, which means the bigger frequency or the higher frequency you get, the capacitor is going to give you less opposition. Okay. Now, when the reactance of a coil equals to the reactance of a capacitor, that's when we call this thing as a resonant frequency. And you might use that in other subjects, but I just want you to know what's going on here. Now, applying a sine wave to the circuit, the voltages across the capacitor and inductor, they are 180 degrees apart. Right? So here's another circuit that we built. Here's the voltage across the capacitor. And here's the voltage that we sense across the inductor. And you can see when one goes down, one is down, the other one is up. And then this one is down, then the other one is up. So they are 180 degrees out of phase. They're 180 degrees apart. This means that the reactances or the oppositions are 180 degrees apart. Now, you might want to play this thing back a few times just to understand this concept. If the resistance opposes a certain way, then the voltage is going to occur a certain way. And if the reactances are 180 degrees apart, then the voltages are going to be 180 degrees apart. Okay? Here. What did I say here? All loads are resistive, capacitive, and inductive. Any component that you have, that you're going to have in your hand, is going to have a certain resistance because it has wires in there. It's built of physical matter, it's built of physical things. Wires are physical things, they're objects. And the wire or metal, it does have certain resistance. However small, but it does have, okay? Now, based on this statement, the behavior of the load in the circuit depends on the type of signal or power applied and the proportions of the load characteristics. Many components are considered to be dominant in a certain way. For example, although a resistor has a certain capacitive and inductive properties, because a resistor is going to have certain capacitance because some of the electrons are going to be stored in a certain way. There's going to be some residues wherever it is because it's a physical object. And it's also going to have certain inductance. However, the inductance and the capacitance in the resistor are so insignificant that we basically just ignore them and we just concentrate on the resistance of the resistor. Okay? So many components considered, okay, although resistor, okay, Okay, I'm going to repeat that. Autoresistor has a certain capacitive and inductive properties. Its resistance is dominant enough that the other two properties can be considered as non-existent. And I just put that in most cases, right? Because there's some extreme cases that some of these things come in play. But we're just going to ignore that. Okay, now the same principle applies to capacitance in capacitor and inductance in inductor. The capacitor is made in a certain way that the capacitance is the dominant factor there. So the capacitance is going to be the biggest thing, and it's going to have certain resistance because it's built of things that are out of metal, but the resistance and the inductance in the capacitor are so small that can be ignored. And same thing, inductance in the inductor, that inductance is the main ingredient in inductor, so the resistance and capacitance are ignored. Okay, so here are a couple of graphs here. Right? Remember when I showed you those voltages here? The voltages, when it comes to frequencies, the voltages are 180 degrees apart. That means the reactances are 180 degrees apart. Now, resistance has no angle. Resistance is a non-reactive quantity, and it does not have an angle. So the angle of the resistance is going to be 0 all the time because it's a linear quantity. Now, reactants, they do have angles. So the reactances are 180 degrees apart, and we can tell that by looking at the voltages across the components. So here's a little graph here. So remember when in inductor, first we would have voltage. Okay. In order to have a voltage, you have to have resistance or reactance that has to be high. Okay, so that means the reactance is high, so it's 90 degrees from 0 here. Okay, 90 degrees up, all the way up. So this is an inductive load. So the inductance is going to be dominant in this part, in this case here. And whatever the load is, it's going to have some capacitive reactance. And because it's 180 degrees apart from that, so of course it's going to go the other way. Okay. Okay. And here is the resistance of the load. Okay. So now, when you subtract, when you basically add those two, right, which basically the magnitude of this plus the magnitude of that, if you ignore the signs, so of course you're going to have XL minus XC, but if you add these two, so this is going to have certain value with a positive in front of it, and this is going to have a certain value with a negative in front of it. So if you just combine these two, you're going to have the total reactance as a magnitude, and it's going to be dominant this way because the inductive reactance is higher. So when you draw a line from that 0 point here into this point, that if you just basically present the total reactance, which here, draw a line from here to here, that's the magnitude of the impedance. So here's the resistance of that under angle of 0. Here's the total reactance of that based on these two. And this line here is the magnitude of impedance. So impedance is a combination of the total resistance on the circuit and the total reactance of the circuit. And that's the magnitude of impedance. And it also has an angle. Now, the same thing here, this is a, excuse me, this is a capacitive load. So of course, the capacitive reactance is going to be higher than the inductive reactance. And of course, the magnitude of the impedance is going to be, it might be the same as far as the length of this vector, but it's going to have a different angle. Now, the impedance formula, Z, stands for impedance, is a square root of resistance square plus the total reactance square. How do we get this formula? It's from this guy. He lived a long time ago. His name was Pythagoras. That's basically the Pythagorean formula. Okay? You might watch this thing a few times. All right. Now, how does that refer to the cables that we're dealing with? Right. So cables also have conductance, resistance. So basically the opposition, the conductance is opposite of resistance. Resistance tells you how hard it opposes whatever the object is, how hard it opposes the current flow, and conductance tells you how easy it conducts the current flow. Right? Okay, so all cables have conductance, capacitance, inductance, which means they have resistance, and they have capacitive reactance, and they have inductive reactance. All that combined, the resistance, and the reactance, and the other reactance, that composes into impedance in a cable. All right. Now, let's go to the characteristic impedance here. Now, you probably don't see that very well, but you're going to be able to see this in the posted lecture notes when you download them in the PDF form. But for the, here's the music. Okay, so now what I did is I just, for the next couple of slides, I magnified this part here so we could read it properly, and I magnified separately that part here. So let's just see what the first part says, okay? A basic capacitor conducts of two metal plates separated by dielectric, and dielectric is another way to call an insulator. The capacitance of a capacitor depends on the size of the plates and the distance between them. That is going to determine the capacitance. The metal plates have certain measurable area. Okay. Of course, it's a statement within a statement here, but hey, there's a reason why I said that. A coaxial cable consists of two conductors, one inside the other. The two conductors share the same center, therefore the cable is called concentric, but the term coaxial ended up being more popular. The conductors are physical objects, and they also have a certain area, and they are separated by a dielectric. So the cable does have capacitive properties. It's just the way it is. The secret here is that we do not use the cable as a capacitor in the circuit, but we do use coaxial cable for the purpose of transmitting radio signals. Right? Again, RG stands for radio guide. For the purpose of radio wave transmissions, we are not interested in the total impedance of the whole length of the cable. Right? Let's say here is that famous cable that we had. Okay, and here's the conductor, and that goes inside, and it's separated by whatever it is. It could be air, or it could be certain type of polymer, plastic. So the longer the cable, if you just had that cable like that, and you just pinch a hole in the jacket thing and connected a wire here, and then you pinched another hole, and you connected a wire into this inner conductor, you're going to have almost something like this, just like a capacitor. Right? Just like that. And the bigger the plates, the longer the cable, the bigger the capacitance of the cable is going to be, and the shorter, the smaller the capacitance of the cable is going to be. However, as I said, we do not use a cable as a capacitor. We don't connect it that way. Okay? That's not the use. What we're interested in is the signal transmission through it. Okay? That's why if we were using that cable as a capacitor, then we would be interested in the total capacitance of the capacitor that we just made out of the cable. But what we're trying to do with this cable is we're trying to insert a wave into this cable. And once the wave is inserted into the cable, it just travels on its own. Just like if you have a little pebble or a rock and you drop it in the water or some lake, the little stone touches the water, so that's the energy transfer, and it just goes down to the bottom, and then there is no motion, there's nothing, but the energy is still there, so the waves travel. Okay, so that's the same principle that I'm trying to convey here. Now, the next slide here. How does the wave travel through the cable? Right? The wave is injected into the cable by a transmitter. So here is a transmitter. Let's say it's some sort of an amplifier that from here all the way to here is our coaxial cable. And over here we have connected an antenna. All right. So what happens is that first the wave is being injected here, and then it travels. Right. Let's just go here like that. The wave is a certain magnitude, and it just goes. And over here, maybe it's going to be a little bit smaller, and over here is going to be a little bit smaller, depending on the length of the cable. So the wave is going to deteriorate because the cable has certain resistance, and there are certain losses over the cable. But here's the idea. And just as a reminder, we're talking about characteristic impedance. Once the wave is inserted into the cable, it travels on its own, right, to the antenna. And then the next wave or pulse is injected, and it travels. So that's basically constantly happening that way. Okay? Yeah. All right. So once the wave is injected to the cable, it travels along the cable under its own energy. The wave will deteriorate, or here's another word for it, attenuate. Attenuation is the signal deterioration. Okay, we got some visitors here. Now, the further it travels along the cable, so the further it goes, the more it's going to deteriorate or attenuate. So the cables have certain attenuation as specifications, and the attenuation is measured per length. It's expressed per length. The transmitter only cares about how hard or easy it is to insert the wave into the cable. So the transmitter only cares about something that's called characteristic impedance of the cable, not the whole impedance of the cable that if we connect it as a capacitor, but characteristic impedance. And characteristic impedance, which is the Z0 or Z0, equals to impedance per 1 meter. Okay. So the total impedance of the cable has nothing to do with the, it has something, but it's not the same thing as the characteristic impedance. The total impedance of the cable would depend on how long the cable is, because you have the plates, imaginary plates, and conductors connected to it. But when it comes to injecting a signal into it, it doesn't matter how long the cable is, because the transmitter does not see the end of the the other end of the cable. It only cares how hard or easy it is to insert that signal into the beginning of the cable, in the interface. And the interface is basically when they touch the output of a transmitter and the input of the connector of the cable. Right? So characteristic impedance does not, and this is going to be on the test, and I need you to understand the concept here. The characteristic impedance does not depend on the length of the cable. Characteristic impedance is not the same thing as the total impedance of the whole object that we have at hand. We are not interested in the whole impedance. We're interested in the impedance per 1 meter of the cable, which is called the characteristic impedance. And here is, okay, so we now there's some terminology if you want to dig deeper into it. Not going to test you on that, but some of the terminology that involves with that is involved with that is also permittivity, which is the resistance to an electric field, and relative permittivity is the permittivity of material of a vacuum. So permittivity is basically that applies to the dielectric that separates the inner and the outer conductor. So the characteristic impedance, let's see, we'll have the formula here. Here is the formula, okay? If you really are interested in that. So Z equals Z0, the characteristic impedance, okay, is 138 divided by square root of K, which K is the relative permittivity of insulation between the conductors, dielectric, times the log of D1 over D2. So the characteristic impedance depends not on the length of the cable, but it depends on the diameter of the outer conductor and the diameter of the inner conductor and the characteristics of the insulator. That's what determines the characteristic impedance. Now, on a job site, you are not going to be asked to measure or find out what the characteristic impedance is of a cable, but I want you to know what it means. And quite often, when you're going to do the tech talk with whoever you're going to talk with when it comes to using coaxial cable, they're not going to say characteristic impedance, they're just going to say impedance. What impedance do you need for whatever you're buying? Okay, so if you want to, if you call some distributor that sells cable and you say, I need some coax, and so I'm going to say, they might ask you, what impedance do you need? Right? They mean the characteristic impedance. And you're not going to have too much to play with, because most of the time you're going to be dealing with the characteristic impedance. The coaxial cables either come with 75 ohms or 50 ohms. These are the basic two types of characteristic impedance that are involved with the cable, coaxial cable. All right. All right, let's keep going here. Your head's smoking yet? All right, so a couple of questions as a review. All right, you might want to watch this thing a couple of times. Now, as I said, all this spiel that I'm giving you right now, you just have to understand that once. And then based on this, whenever you're dealing with structured cabling or connecting equipment, you're just going to say, okay, 50 ohms or 70 ohms, but now you know what you're talking about, instead of just having those imaginary numbers from wherever, kind of a cloud that somebody's talking to you, okay? All right, so a couple of review questions here. Will the characteristic impedance change if the total length of a coaxial link changes? Great. All right. I guess I guess I did a good job to explaining that. Okay, cool. Now, why do we need to match? Okay, so here's another concept here. When it comes to the impedances, why do we need to know the characteristic impedance of a cable? Well, in other subjects, you're going to study something as a maximum power transfer. And pay attention to this. And that's going to give you a little bit of understanding. If you have already studied that, or will you study that in the other subjects, here's the idea of maximum power transfer. The impedance, the output impedance of this amplifier has to match the characteristic impedance of the cable. And of course, it has to match the impedance of the whatever receives. It could be another amplifier, or it could be another receiver, or it could be antenna, or it could be a television set. So for the maximum power transfer, you need to have the impedance of the output of this equipment equal to the impedance of the input of whatever it is. In this case, it's a coaxial cable. All the impedances have to match. Right? So if you have an amplifier, a radio frequency amplifier, that has an output of 50 ohms, you need to use a cable that is 50 ohms characteristic impedance. If whatever it is, 75, you get the idea. Right? Why is it so important for the maximum power transfer? And I hate to use the analogy of water when explaining electricity or principles of electricity or electronics. But in this case, I think it's the best way to use what to use the water analogy. Okay? Let's say there's a water pipe. It has a certain diameter, and it has to be joined with another pipe that has to conduct the same water flow, the same amount, the same volume, at the same speed. The water has to flow from one to another. Of course, you have to get the same diameters in order for this thing to be uninterrupted, to have uninterrupted flow. What happens if the diameters are different? Right? If there you go. If you have a certain size diameter of pipe that needs to transfer the water uninterruptedly, and let's say you're going to have a thinner pipe connected to it. Of course, the thinner pipe is not going to be able to transfer as much water into the other pipe. Okay, so the water flow is going to be interrupted. So maximum power transfer, the whole power is not going to be transferred to the thinner pipe because the thinner pipe is just incapable of carrying that load. What's going to happen is that whatever is trying to pump that water is going to be put under stress because some of that is going to start bouncing back on it. And as a result of that, you're going to have some energy buildup, and that's going to result in heat buildup. So that's one way. Let's see what happens if you have things going the other way. In order to have a proper flow of the fluids through two pipes, let's say we have a thick pipe on this side, and we connect a little tiny pipe into it. Do you think that this water is going to flow the same way through the big pipe? No, of course it's not going to go. The water is just going to go down here, and it's just going to start accumulating. So you don't get the maximum power transfer. It's just basically the whole system is not going to be efficient. All right. So that's why you need to match the impedances of whatever is transmitting the signal, whatever is carrying the signal, and whatever is receiving the signal for the maximum power transfer for this thing to be the most efficient. Then we need to have the impedances equal. All right, so now here's 1 o'clock, and we have till 2 o'clock. Do you guys want to take 5 minutes or 7 minutes to take a break, go to the washroom, and pour yourself a fresh coffee or something like that? We should do that. Okay, so I'm just going to, okay, let's see, what is the time on my phone? My phone shows, well, let's say it shows 1 o'clock. So let's meet back here at, let's say, 7 after 1. Okay, and we're going to just continue and just going to continue the lesson, the second part of this lesson. Okay. Okay, headphones on. Right, are we ready? It's 7 after 1. Let's keep going. We still have a lot to cover. Okay, can you guys hear me? Okay, good. Thank you. Sip of coffee. All right. All right. So the questions: why do we need to match the impedances as we interface different parts of the whole transmission system? And the answer is 3 words. Anybody? The reasoning for that is maximum power transfer. Thank you. Okay. If I had a candy, I will give it to you, but I don't have one. I ate it. All right. Can you go over one question again? Question number 1. Okay. Will the characteristic impedance change if the total coaxial cable length changes the length? All right. Yeah, because the characteristic impedance does not depend on the length of the cable. It depends on the inner diameter of the inner conductor, diameter of the outer conductor, and the characteristics of the insulator. That's all it depends on. The characteristic impedance is impedance per meter, right? So if you have a 10-foot long coaxial cable, the impedance per meter is going to be certain way. And if it's the same cable, if you have 100 foot of that same cable, the impedance per meter is going to be the same. Okay, so this characteristic impedance is the impedance per meter. Okay. All right. Okay, let's keep going here. Coaxial cable applications. Now I have included the RG58 here. Okay. Now RG59, it used to be used in the network cabling. So the computers or the LAN networks used to utilize coaxial cable. That was happening till the mid 90s, the early 90s, and then the twisted pair took over. Okay. So that's in the past. Now the video signal still has some uses. You can transport video signal over coaxial cable. That used to be the old style security cameras or CCTV, closed circuit television. But it's mostly in the past. Okay, now everything has gone digital. Now amateur radio, that's still going strong. Okay, when there's some radio hobbyists, that RG59 is being used. Also, RG58. Actually, RG58 is more popular with amateur radio because most of the transceivers or transmitters and receivers that are involved with amateur radio, they want to use 50 ohm, and the characteristic impedance of the RG58 is 50 ohms, and the characteristic impedance of RG59 is 75 ohms. Okay. The frequency limit, the bandwidth. What I mean by that is that how high of a frequency signal you can send on one end, and the cable is going to handle that, keep the integrity of the signal that is understood by whatever the equipment on the other end. How high frequency can you pass through that cable when it comes to analog signal, which is basically radio signal, radio frequencies in megahertz or in kilohertz. Right? So the frequency limit of RG59 is, okay, so here's, I put 1000 megahertz, which is basically 1 gigahertz. But when you do the tech talk with people in communications, telecommunications, they're going to tell you 1000 megahertz. Where's my mouse? Here's my mouse. It's going to, because it just so happens that the frequencies are specified in megahertz. It's just that popular talk that they're going to say 1000 megahertz instead of 1 gig when it comes to coaxial cable. When it comes to twisted pair, then it's a free game. Usually you're going to specify in gigahertz, okay? But it's just a, just a nuance, just a little bit of a detail, okay? So the frequency limit is 1 gigahertz or 1000 megahertz. RG6, which is the one that you most likely are going to see if somebody installs the cable modem in your house. That's the thickness of the cable. It's mostly used in cable television, mostly in the past, because the cable television is being kicked out by the digital television here. Right? Now, in CCTV, CCTV stands for closed circuit television system, closed circuit TV. And in today's meaning, that basically is the security cameras or the security surveillance. Now, this will be the older version of the security cameras that they would use a coaxial cable to provide the video signal, and they will have a separate power cable connecting to the camera, supplying power. You are still going to see some of the old systems here and there, but you're going to see less and less of that. And sometimes okay, so the equipment is still available for sale for this type of signal, for this type of cameras, if you want to retrofit a system. Let's say somebody has a security camera system in whatever building that it still works, and it's just going to be too much work, or they just don't want to spend the money on replacing the whole cable infrastructure, because the security cameras right now, they use Cat5e cable at the most. I mean, at least, yes, you can use Cat6, of course, but most of the cameras run on Cat5e. So if you want to get the totally new system, you would have to replace all the cameras, and you have to replace all the cabling, and you have to replace the head end, in order to get the whole system up to date. Or if you install a new system, that's the way you would install, right? You would just run Cat5e cables to all the cameras, and you would use PoE, power over Ethernet, to supply the power, and also the cable would convey the signal. But you might get in a situation that there's an old system still intact, but the head end is not really working. Maybe something happened. Maybe the hard drive went. Maybe something went wrong with that, and the retrofitting would be just buying just the head end and connecting that thing to the already existing cameras. So somebody wants to save money. You're going to have situations like that, all right? So that's RG6. Now, internet, broadband, and we're going to talk about, see, I put this word here in like an amber kind of a color or yellow, because we're going to talk about that in the next few slides, right? What the difference between broadband and baseband. How does HDMI compare to coaxial? It's a different type of HDMI and coaxial. There are two different worlds. Yes, they use copper cables, but HDMI has a different signal protocol, and just the signal is in different shape and form than the coaxial cable. Right? The HDMI has a limit, length limit. The coaxial cable also has a length limit, but it has it can be much longer. And then through coaxial cable, you most likely would send a module. You could actually send a modulated signal, which we're going to talk about that in next few slides as well. The HDMI cable is basically pure video signal instead of a video signal that's modulated onto another carrier wave. Okay? All right, so it's also RG6 also is in antennas. Frequency limit here, you see we have pretty much the same thing. Frequency limit is 1000 megahertz, 1 gigahertz, and the characteristic impedance is 75 ohms. So according to these two pieces of information, there's no difference between the specifications of that. However, the RG6 can carry the signal over longer distances. The signal does not deteriorate as much in the RG6 as it would in RG59. Okay? Then there's RG11, which is the thickest of these, all of these. And cable television, same thing, mostly in the past. as far as cable television, it also was used. Maybe some of you guys would go to some elementary schools or high schools where you would see the televisions in each classroom. There would be those big television sets. Some of those schools still have that. And that would also be considered as closed circuit television system. The signal would be modulated onto the coaxial cable, which would be the main cable. It most likely would be RG11 because RG11 has the least losses out of all those because it's thickest. It uses more copper, so it's basically has less resistance, physical resistance. So the signal doesn't deteriorate as much in RG11 as in RG6 or RG59 or RG58. Okay. Then from that you would get the main signal in RG11 here, and this would be the amplifier here going, injecting the signal this way here, and we have somebody knocking at the door. So then from here, there would be the main very powerful signal going through the RG11, and that would be in the hallway somewhere in the ceiling. And then over here, you would have, there's a parcel. Over here, you would have something like a tap, okay? That would just sample a little bit of a signal, and the tap would have a certain value that would just basically just take a sample of that signal and send it to a specific television set in the classroom. And then again, you would just have another tap and you would have another so that's also was called closed circuit television system. And sometimes you're going to still encounter some of those systems as if you go for service calls, if you work for different communications companies, you will encounter some of those systems. Okay? So that also means the closed circuit television system. Okay. Now, also the RG11 is used for the internet, broadband, and we very soon will know what that means. Antennas and the frequency limit. Okay, see, it's a higher bandwidth. You can. It's basically 3 times as much, and the characteristic impedance is 75 ohms. And then there's the RG58, which mostly is used for the amateur radio. Not way more this year. You're going to see RG58 for antennas if somebody has a ham radio. Hobbyists using the amateur radio communications, because most of the equipment that involves amateur radio, they involve 50 ohms output impedance of the transmitters, okay, and the receivers. If you want to know more, click here. Here's a nice YouTube video that I found on the internet. Now, this guy is amateur radio enthusiast, and he's very knowledgeable as well. So, if you want to know more, click on that when you download this PDF presentation. Is it mostly used because of the higher frequency limit? Which one? Which one do you mean? RG58? For the ham radio. Okay, no, it's basically RG58 is because of the characteristics. That's the key ingredient right here, the 50 ohms for the maximum power transfer. Plus, when it comes to antenna, you're not using so much length of it. Maybe you're going to use 50 feet, 60 feet sometimes, and that's pretty much it. So the signal deterioration that's not coming to play as much. Plus, you're not supplying multiple receivers with that, multiple pieces of equipment. It just goes to that antenna, one antenna. So if you get output impedance of a transmitter, match that with this, and match it with the antenna, then you got a very efficient system here. Okay. All right, now, here's the other ingredient when it comes to when it comes to the coaxial cables. Okay, so what do we have in this table here? We have a frequency. We're going to talk about attenuation, and of course, it's specified at certain temperature, because temperature might play a role in that as well. And again, attenuation is signal deterioration. Okay. Now, here's the frequency in megahertz. So here's the lower frequencies, there are higher frequencies. So 5 megahertz up to like 3,500 megahertz. And here is RG58, RG6, RG11, and I didn't list the RG58 here, but if you want, you can Google that if you wish. Our Wi-Fi 5G net is the same thing as the frequency in megahertz. No, 5G is it's basically it's called 5th generation, and there are certain specifications that come with that. Okay? So 3G is the 3rd generation. It's basically as the technology advances, they have a system that's implemented of certain specifications, and they just call it by generations. Yeah. Now, RG59 is the lowest of the three. There's RG6 in the middle and then RG11. So you could see here, this is the deterioration or attenuation in decibels per 100 feet. Okay, I'm not going to go into the decibels too much, but one thing I want you to understand here, if you have a power that is specified in decibels, it could be power of a radio signal, it could be power of the audio volume that's pumping out of the speakers. Okay? So here's something that's going to give you some idea of what means as far as the decibels, because decibels is a reference scale, and you will understand when I'm done with this here what that means. Okay, let's say you have a signal that is 100 watts. Okay? If you're talking about the power, not talking about the voltage peak to peak, because that's different. When you talk about power, and if you raise the power 3 decibels, you're doubling the power of the signal. Right? Now, if you lower the signal 3 decibels, you're cutting the power in half. So if you have a 100-watt signal, you raise it 3 dB, you get 200 watts. You lower it 3 dB, you get 50 watts. Okay. Now, if you have a 200-watt signal, you raise it 3 dB, you'll have a 400-watt signal, and so on. So that's how the decibel scale works. Okay. So over here, oops, where's my, okay, here it is. So at 5 megahertz, you can see that the one thing that's common to all of those is that the higher the frequencies, the more loss you get. Okay, the lower frequencies, they pump through with a lot of energy. They have a lot of energy. They can carry through a long distance with little loss. Now, the problem is with the higher frequencies, they don't have as much energy, and as they travel through the cable, they get deteriorated quicker than the lower frequencies. See here? So let's see, our G59, here's one per 100 feet, or the other one's per 100 meters, whichever you choose. So let's look at the feet here. So 5 megahertz is going to attenuate 0.89 dB per 100 feet. Okay. Every 100 feet, you're going to get well, basically almost 1 dB, so 0.9 dB loss. Now, when you have the high frequencies here, per 100 feet, you're going to lose 16 dB. Remember, 3 dB is half of the signal. So 16 dB is, well, you just do the calculation here, right? Now, so here is RG59. All right, so now, if you go RG6, it doesn't attenuate the signal as much as RG59. So if you were talking about longer distances and weaker signals, you might want to get the better cable, but it also costs more. Right? Per 100 feet, 5 megahertz, RG6 is going to give you 0.7 as opposed to 0.9 dBs, right? And less deterioration, less attenuation for the higher frequencies. Now look at this RG11, which is the thickest of them all, and it has the least amount of attenuation. of them all. So per 100 feet, the high frequencies are going to get attenuated 8 dBs as opposed to 16. So you get less loss here per 100 feet than RG59 and RG6. You see that? Yeah, these three. So that's basically, depending on what application you're going to have. RG59 are, sorry, RG11s are mostly being used if you have just like a main signal supply. And if you want to top off from that main trunk, if you will, then you can put a top in line with that cable, and the top is going to carry lower signal. And then if you have a shorter distance, then you can use RG6 still, as long as the impedance is matched. But RG59, RG6, and RG11, they all have 75 ohm characteristic impedance. So you can basically use them, you can combine these cables in one system. Okay? So that's as far as attenuation. Notice, here's a key thing for next slide here. Higher frequencies attenuate more than lower frequencies. Lower frequencies can travel further without loss, as much loss as the higher frequencies. Higher frequencies don't have as much energy to carry through longer distances as the low frequencies do. Okay, so keep that in the back of your mind here. All right. Now, I'm not going to go too much to that. However, there are some frequency bands, and these are the television channels here. Yeah. Television channel 2 to 13, like that. Yeah, okay. So let's say if you're talking about the cable television, channel 2 has a bandwidth of between 54 and 60 megahertz. So you can see that it has 6 megahertz. It needs about 6 megahertz of space to carry different signals that are involved in transmitting channel 2. So on one, okay. So let's say here's that lower frequency here and the higher frequency of that one channel. So there's between here and here, you're going to have 6 megahertz difference. And at some point, you're going to have a video signal. And at some point here, you're going to have an audio signal and so on. And there's different synchronization signals and stuff like that. Okay, so that's basically channel one of the channels. Okay, then another channel is going to have another, it's also going to carry over the 6 megahertz, and that is going to be same proportional frequencies as when it comes to employing that bandwidth that's assigned for that channel. So if you look at this here, every channel has 6 megahertz bandwidth here. 66, 72, and so on. It's going, the difference between the higher and the lower is going to be 6 megahertz. So that's how the channel TV, the cable TV channels work. And then, of course, there is the broader picture here as far as that. So not a big philosophy here when it comes to that. We're not going to go too deep into this. Now, here is something that's called an RF amplifier. Right? So here's the idea of that. Let's say you're going to have one of the older systems that is still in use in one of the schools or bigger facilities, mostly at the schools, and some of them are still intact. Because let's say 10 years ago, they spent $200,000 on installing it, and they're going to try to get as much mileage of it as they possibly can. So let's say here, they have, can we see it here? Yeah, okay. So this would be this amplifier here with the cable TV signal coming from the city. Right? So that's the signal coming in. this would be this. That would be this amplifier here, this little triangle. Okay? So that's the amp, RF amp, radio frequency amp. Okay. Now from here, we're going to go and put in the ceiling RG11. Okay. And this is the hallway, and this will be the classrooms around the hallway here. So let's say this classroom here, this signal has a certain type of strength here because per 100 feet, the signal is going to deteriorate so much. We're going to put something that's called a tap, like tapping in. And from here, the tap is going to have a certain value that's going to get certain amount of decibels out of the whole thing, and it's going to pass through to the television set. Then there's going to be another tap, let's say 20 feet more, or 50 feet more, or 100 feet more. It's going to be another tap. And there's going to be another cable here going into another television set, TV, all right? And so on and so on. Right? So RG11, although it has less loss than RG6, it's still going to have certain signal loss as you travel down the length. And remember when I said the higher frequencies deteriorate more than the lower frequencies? Still keep that in the back of your mind. So here are the controls of an RF amp. Here's the input that the signal travels through from the city. That's the input. And let's say it has, I don't know, maybe 6 dB strength. Then after that, you're going to raise the amplifier, you're going to raise the volume or the gain. Yeah, you can control that. So the signal has a certain strength at the output of this amplifier that is injected of a certain strength over the whole system. Now it has to have enough strength to carry the furthest TV. Right? Here's the thing, because, and over here, by the way, this would be RG11 cable. This could be RG6 or RG59, because over from here to here you might have 200, 300 feet, and from here to here you might just like 40 feet, right? So that's fine. So when the higher frequencies get lost more over the distance, what you're going to have at the end of the run, you're going to have the lower channels coming out nice and clear on the television set, and the higher channels might get a little bit snowy because the frequencies, the higher frequencies utilize more the higher channels, of course. So the higher channels are going to come a little bit weaker than the lower frequencies. So here are the controls. Here's the gain. You raise the whole gain of the whole system. And when you get to the end, you adjust something that's called a slope, or sometimes it's called a tilt. What the idea of that is that at the beginning of the amplifier, you tend to amplify the higher frequencies more than the lower frequencies. So when it gets to the end, this thing kind of equalizes as the frequency. So then you get clear channels on all across the spectrum, all the channels. So that's why when you adjust the controls of the RF amplifier, you have to have a good balance between the gain of the whole system and the slope of the whole system. So you have the input of that, you have the output of the amplifier, and over here you have a minus 20 dB test signal, so you could just connect your control television set just to see what's going in. And here you can just grab a minus 20 dB test signal on the output just to see what's coming out of the amplifier. Right? And by the way, you just you're going to see some other pieces of equipment when it comes to those old systems. You're going to see something like filters. Right? Because let's say there's the whole cable TV coming in from the city, and the school is going to have little TV studio, broadcast TV studio, and they want to also inject that after the amplifier. All right. Or the best would be before the amplifier. Here. So you got the channel combiner. So here's the channel combiner that combines all the signals. All right. That's a combiner here. And you get the signal from the city going through a filter that you're going to filter out, let's say channel 56, 57, and 58. So those channels are going to be eliminated from the whole cable TV coming from here, and it's going to go into here. So minus channel, like let's say 58, 59, and 60. Okay, minus. So those channels are not going to be existing there. And over here, you're going to inject your little broadcasting studio for your high school that is going to broadcast on channel 58, 59, and 60. And at the end of that, you're going to have the whole cable TV with those channels from your broadcasting studio. And you need to eliminate those just so they don't bite with each other. So if you combine this and that still existing, you're going to have one poking through the other, things like that, right? So I just wanted you to see that this is the type of equipment you might see in the old system settings that are still being used. And not all the time you're going to have new installations. Quite often you're going to be sent for something that's called service calls. And the more jobs you can do, the more capable you are, the more employable you are. Right? 139. We still have time. We're good. Okay. And there's the link. Here's the link to the North American television frequencies as far as the channels. If you're interested, you can just watch that. Okay. Now, here's the second part. Because what do we use that coaxial cable for? Is internet. Okay. Now, broadband connection versus baseband connection or signal transmission. Broadband internet service is the most used form of internet access because of its high access speed, high speed. Okay. So the cable modem is going to carry a lot more megabits per second than the DSL provider, right? Now, it is offered in 4 different forms, broadband. Okay. Broadband signal can be transported over DSL, which is the telephone line, digital subscribers line. Remember dry loop? That's just a DSL without voice, or you could have both voice and DSL on the telephone cable. The broadband can be carried over the fiber optics or the optical fiber or cable, which is the coaxial cable, or through satellite. Now, the old dial-up modem connections, the dial-up connection is the only non-broadband internet service available. And just keep listening and it's all going to make sense. And even though it is cheaper, less expensive, most internet users are moving towards the faster broadband, well, of course, internet connection. Right. Now, here's the concept that we also need to understand, that Ethernet, which is the LAN signal, that's the signal that is provided from your switch in your LAN straight to your computers, or from the modem or from the router into your computers. It's a digital type of signal. right? And the best delivery is time division multiplexing or baseband, internet signal that is coming from the outside of your house into your house is analog signal, and the best delivery will be frequency division multiplexing or broadband. What's multiplexing? Well, multiplexing could be different, could have different forms. It could be time division multiplexing. Let's say you have a link and you have different points. And this, let's say it's a telephone link, okay? This would be one telephone here. This would be another telephone here. There's be another telephone here. And there'll be another telephone here, another telephone here, another telephone here. And somehow they whichever way they talk to each other. So here's that one common wire. Okay? And those are going to the telephone subscribers here. And then you have something like a dial, mechanical dial, two of those. If there's a connection established between this telephone and that telephone, of course, that is going to go like this. All right, that's how those things will be connected. If this telephone goes through that, then this would how they will be connected. Problem is that you only have two wires. Okay? Okay. Now, let's say, but you have 3 or maybe 15 subscribers transferred over those two wires only. So you connect one to this one, and these guys are talking. Then you connect this one to that one, and these guys are talking. Then you connect this one to that one, and these guys are talking. Now, if you make this thing switch at a very fast speed, and if they're synchronized, then it's going to sound, all those breaks are not going to be noticed, all the switching is not going to be noticed because switching is going to be happening very fast. Then those people are just going to think that they have a continuous connection. So that's time division multiplexing. Right? Everyone to the other is connected one link at a time, but they're switching. The switching is happening very fast. So so they are going to hear as if they're having a separate connections, right? But those things have to be synchronized. So that's called time division multiplexing. Okay. Now, there's also a frequency division multiplexing. When, let's say, you have one link, let's say there is a coaxial cable link. And over here, you have splitters. So the splitter goes into one of the houses here, and it goes to the other house, it goes to another house, and so on. And here's, let's say, a TV station that is injecting all the channels, like let's say 100 channels, and all are injected into this one cable. So all are present at the same time. So when, let's say, this house wants to watch channel 5, they would have a tuner that would tune in to only the frequency that is in the cable. All of them are happening at the same time, but this is going to only tune and listen to only all the frequencies that are associated with channel 5. Let's say this one wants to watch channel 7. It is going to tune into only channel 7 that is present here, It's going to receive all of these. Those are going to be present here, but it's only going to listen to that channel 7 or to watch channel 7 and so on. So all the frequencies are being present in this cable, but the tuning happens. The receiver tunes into which frequency they want to receive. So that's called a frequency division multiplexing, as opposed to time division multiplexing. Love that train. Almost done here. You get a good dose of a red pill today, eh? All right, keep going. So now, when you look at this thing here, you understand what that means. You might want to watch it again. Okay. Broadband versus baseband. Broadband. All connections are divided into channels. With the baseband, no channel division, just one signal at a time, and the timing is synchronized. Who receives what at what time? Time division multiplexing. Okay? Broadband, each channel occupies a space within the all spectrum of the medium, like for example, cable. What would be a example of another medium? It would be the air. There would be a radio station that transmits all the frequencies, all the stations through one antenna, or there could be different antennas transmitting different frequencies. The air combines, the air contains all of them. You're driving in your car, you tune on to specific radio station. Here's your frequency division multiplexing. Okay? So the air contains all the frequencies, or the cable contains all the frequencies. Right? So each channel occupies a space within all the spectrum of the medium. It could be a cable that the medium can handle. Now, comparing to baseband, each communication link occupies all the bandwidth that the medium can handle. So each communication link. So let's say you don't need to have, when you have a time division multiplexing or baseband, you don't need to have a cable that is capable of all the frequencies. You just need to have a cable that is capable of transmitting one channel. That's the bandwidth you need to be transferred to that cable, because the time switching happens. One listens to just one client at a time, and the switching happens all the time, synchronously. Right? Broadband communications between devices is established through tuning into a specific frequency. With the baseband, no tuning is involved because the signals are not assigned to channels. Right? So with the broadband, you would have frequency division multiplexing, and with the baseband, you would have time division multiplexing. And remember what I said? The internet signal, for example, that goes into your house, it is a digital signal, but it is modulated in an analog way. So you get an analog signal, you get the frequencies, just like TV channels. When it gets to your house, it's being transferred onto a digital signal, and then that digital signal is delivered to your computer or cell phone or camera or whatever else. So here are the examples of, there's a MUX, there's a multiplexer and demultiplexer that is being involved. So here's the example of a broadband that the link carries all the channels at once, and they are multiplexed in that way, and they are demultiplexed or deciphered by a tuner. Just the receiver sees all of them at once and just decides which one to listen to. Now, here is a baseband. That's the time division multiplexing. You would carry Like say there's 1, 2, 3, and 4 channels here, 1, 2, 3, and 4 channels here. Only one channel is transmitted at a time, and the demultiplexer basically listens to only the signal only at those times that it's supposed to listen, and it ignores all the other times. And when it happens very fast, it's going to look like the whole signal is continuous. So that's the difference between frequency division multiplexing and time division multiplexing. This is what's happening, what's coming into your house through your cable modem, or cable through the coaxial cable internet service, or fiber optic lines, or the DSL. That's what's coming into your house in this form. The modem transfer that. Okay, modem, multiplexing and demultiplexing. If you combine these two words together, you're going to get modem. Right? Modulate and demodulate. Those two words combined together, they form the word modem. So signal is modulated on this way here, and it demodulates that, and it transfers that signal into this kind of form. All right. Now, one more thing. Here's the dial-up connection. This signal, because in order for your internet signal to come to your house, it has to be modulated onto some sort of a carrier, and that carrier is going to be received, and it's going to be translated into the digital signals that goes through your house. So time division multiplexing is used when, so here's the frequency division multiplexing, or when it comes to delivering through the cable modem or cable delivery, or DSL, digital subscribers line. There's another way of connecting your computer or whatever device or your network to whatever else that you want to establish the link, and it's called a dial-up connection. The dial-up modem basically dials a telephone number of the receiver, and it establishes direct connection. That is the slowest possible internet signal that you can get. It used to be popular when the internet was being implemented, which is early 90s. That was the thing to do. Or 80s, I also would use modem. If you watch the movie that's called War Games, you're going to see that, okay? Now, most of us would think that that's already in the past. However, this thing is still being used, okay? Where is this thing being used? The dial-up connections are being used as backup systems. And the most popular use for the dial-up backup systems are in retail. Let's say you have a store that has 5 cash registers, and all those cash registers are on the network. They're connected to the main network, and that through VPN, remember, they're connected to the main whatever frame, that could be in a different city of whatever the franchise is or whatever the business is. Okay. So when everything is nice and smooth, the network is operational, things are going fine, the transactions are going through the cash registers, and everything works fine. Let's say the network goes down. The router goes down. Something happens to the network. The network there's no more internet, right? But the store still needs to make sales. So what happens is that the whole system has a backup system that switches automatically switches to the dial-up connection. And the dial-up connection, every time there is a debit transaction, that is going to use the debit machine is going to use that dial modem to dial to the server, to the whichever is pre-programmed, and it's going to establish a telephone connection, make the transaction, and hang up. So when the store has like 5 cash registers, all 4 cash registers are going to be shut down. There's going to be one designated as a backup, like emergency kind of a thing. So there's going to be only one cash register that is going to be available for the clients to use. The transactions are going to go much slower, because right now, if you use a debit, if this thing is a network, you swipe it, put your whatever, and this thing goes almost instantaneously, right? But with the dial-up, it has to use the modem, dial up, make a connection, make a transaction, and hang up. So it's going to be slower, but the store can still make the sales. So that's why it's a very popular system. Most of the thing people say that, yeah, you know, the dial-up is not used because it's not used in the residential. You're not going to use dial-up connections. However, in commercial systems, if you're going to be sent to service calls, you might have to service some of those. So that's how the dial-up modem works, right? And this is what you would see in a rack. Okay, you would see the patch panel. This would be the field wiring, and we remember what field wiring is. This would be whatever the modem that is connecting things to the internet, and here's the router or gateway, whatever it is. Here's the switch. So the whole network is the part of, and right somewhere on the bottom there, you're going to see one of those. US Robotics, most of the time, dial-up modem. And sometimes you're going to be asked to, maybe let's say the router goes bad. You're going to be sent to replace the router, and it's going to be sent to you. You're going to send the store, you're going to replace that. But when you go there, this thing is already going to be operating. Or sometimes what you're going to do as service calls, you are going to be sent to do the backup modem test. So it's going to be a regular periodical type of service call that is going to be scheduled. You're going to arrive there and you're going to say, okay, I'm just here to just do the test in case something happens, just to make sure that this still works, right? So that's basically today's lesson. All right. Any questions so far? I expect that you not going to have too many questions, because I think your heads are smoking now. But when you go over those notes, you're going to be able to grasp the whole thing. And of course, it's going to be on YouTube, so you can watch it as many times as you want. All right. You need more coffee. All right. Yeah. This lesson was slightly different than all the lessons, because we just had, all those things that I needed to put together. They're kind of interconnected. It's just as one bundle. I had to put them together in this one 2-hour lesson. Okay. So I apologize if it was too much, but if you grasp the content, it's not going to be that bad. It's pretty all it's all logic there. Right? All right, cool. So that's pretty much it for today. No more questions, and I'm going to communicate with you on how the test is going to be conducted. You have had me last term, so pretty much you know how I do my tests. It's going to be deployed next week. All right, so watch for the emails, watch for the announcements for the online test. Okay, thank you very much, and that was it for today.